Hey, this is Dr. Mittal. Unfortunately, I'm not here for Lesson 15 to give you the WPR 1 review. However, I put together a quick video that will summarize all the key things to help set you up for success for the WPR. As a general reminder, WPR 1 will be on Thursday, and it will be in class 55 minutes. It's worth 125 points, so it's worth a lot. Keep in mind you're allowed a 3x5 handwritten note card front and back. You will need to submit your note card with the test. It covers lesson 1 through 14, so everything that we did, including what we did in the lab just now. Keep in mind we will not ask you to use precision tree. However, you will be expected to look at a diagram, whether it's a sensitivity analysis or a decision tree or an influence diagram that comes from precision tree, and be able to interpret it. So this slide goes through a very high-level overview of what you're expected to know. This is basically comes from our lesson objectives from lessons 1 through 14. So things like, what is a decision? 6 elements of decision quality, quality versus outcome quality, decision analysis flowchart, probabilities, modeling decision problems, influence diagrams, everybody's favorite, decision trees, and kind of converting decision trees to and from influence diagrams, along with sensitivity analyses. So a couple of definitions that we need to make sure that you know really well: decision and decision analysis. So decision is an irrevocable allocation of resources. This means that once you make a decision, there's no wish-wash, there's no taking it back. You are on a path and you're taking it. Now, decision analysis is a set of tools that allows us to be able to make sure that we make the best decisions possible to help increase our likelihoods of having a good outcome. So when we start looking at decision quality, there are six things that we have to make sure a good decision has. We have a frame, we have the preferences, we have the information, we have alternatives, we have logic, and we have commitment. Hey, so I love this diagram. I love all this because I think this sums up a lot of the essence of decision science right here, in that a good decision, we make good decisions, we do decision analysis to try to increase the quality of our decision and to have a good decision. And if we make a good decision, it's expected that we have a good outcome. However, it is not guaranteed. You could get unlucky and you might have a bad outcome. Similarly, you might make a bad decision. You might just not do any analysis at all and just make a bad decision, and you might have a good outcome. And that's just what happens if you get lucky. But again, decision analysis is all about helping you make a good decision so that it's expected that you have a good outcome. So we talked about the decision analysis flowchart, and this is straight from the book, chapter 1, page 9. But there's a series of steps that we can do to make sure that we make the right decisions. So identify the decision situation and understand the objectives. Identify the alternatives. Decompose and model the problem. Choose the best alternative. Sensitivity analysis. That's a big one. Make sure you do the sensitivity analysis. Decide if you need more analysis. Yes, then move back up and repeat. If not, implement the chosen alternative. One of the 6 elements of a good decision are your alternatives. Every decision requires alternatives, and you just derive your alternatives from values. So when we start looking at value-focused thinking, again, this is similar to what we teach in SE301, we're trying to develop our alternatives using value-focused thinking. There are 3 approaches we can use. The first is the fundamental objective approach, which uses a value hierarchy, and this is similar to, again, what we use in SE301. You develop your value hierarchy that's derived out from your fundamental objective, look at your functions, your objectives, your value measures, and then look at how you're going to meet those value measures. We can also use what's called a means objective network. And this is where we look at our fundamental objective, and then we have our means objectives, where we look at, well, we're trying to accomplish A. Well, how are we going to do that? Well, we have these sub-objectives, and then we continually decompose that until we have a understanding of what we can do to meet those sub-objectives. The third is a strategy table. The strategy table is similar to Zwicky's morphological box that we teach in SE301, but it's where you look at your different design decision parameters and you pick one item from each column. Again, it's called a strategy table for this class. So we spent a full lesson talking about probability and just focusing on these 7 rules right here. So again, make sure your probabilities lie between 0 and 1. Your mutually exclusive probabilities must add up. Your total probabilities must equal 1 for them to be collectively exhaustive. A requirement for conditional probabilities is the probability of A given B is equal to the intersection of A and B divided by the probability of B. If you have 2 events that are independent, and we'll look at number 5 on here, if A and B are independent, then the probability of A given B is just the same as the probability of A, because it really doesn't matter what happens with B. Again, and also number 6, we have complements, so the probability of not A is equal to 1 minus probability of A. Probability of not A given B is equal to 1 minus the probability of A given B. We also have the total probabilities, number 7, and again, this makes a lot more sense if you actually draw out your probabilities. The probability of A is equal to the probability of A intersect B plus probability of A intersecting not B. That makes sense. And similarly, probability of A is the same thing as probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. And this feeds into Bayes' theorem. Joint probability tables are an incredibly useful tool for understanding probabilities, especially when you're looking at intersections. So right here we have 2 scenarios. The first is we have the probability of A being 0.4, probability of B being 0.5, and the probability of A intersect B being 0.2. So right off the bat, you can tell that A and B are independent of each other because 0.4 times 0.5 is 0.2. So the probability of A intersect B is the same as is equal to probability of A times probability of B, which implies independence. Now, coming down to our joint probability table, we know that the probability of A is going to be 0.4. So we can put a 0.4 on, at the bottom of the table to indicate the probability of A is 0.4. Now, if the probability of A is 0.4, we know the probability of not A is 0.6. Now, similarly, we know the probability of B is 0.5. That's given to you. So probability of not B is also going to be 0.5, so that they sum to 1. Now, if we know that the intersection of A and B is 0.2, we now know that the probability of A intersecting not B is also 0.2 because they have to sum to 0.4. Meanwhile, the probability of the intersection of B and not A is going to be 0.3 because the probability of A intersecting B plus the probability of not A intersecting B has to sum to 0.5. Similarly, the probability of not A intersecting not B has to be 0.3. Over on the right, we see scenario 2. Here we see a case where they are not independent because the probability of A intersect B is 0.35. It would need to be 0.2 if they were independent. So looking at our joint probability table, we can set it up almost identically to how we just did it, but the numbers inside will be slightly different. So again, A is 0.4, not A is 0.6, B is 0.5, not B is 0.5. A intersect B is 0.35, so A intersect not B has to be 0.05 to sum to 0.4. Meanwhile, the intersection of not A and B has to be 0.15 in order for the probability of B to sum to 0.5, and the probability of not A and not B has to be 0.45, so that again the probability of not B sums to 0.5. So we spent a good amount of time in the class talking about Bayes' theorem. We spent all of lesson 3 on it, and we had a quiz where this was asked. It was also on the homework assignment. So good amount of time spent on Bayes' theorem. And what we looked at with Bayes' theorem is the probability of B given A, if we know the probability of A given B, as well as the probability of B and the probability of A. If we don't know the probability of A, because sometimes that's not quite given, you can decompose that into the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. And this helps set things up so it's a little bit easier to work out what the probability of B given A is. So we've done a lot of probability and some of the more common mistakes that we saw. So first off, the probability of not A given B is equal to 1 minus the probability of A given B. It is not equal to, however, the probability of A given not B is not equal to 1 minus the probability of A given B. So just make sure you keep that straight in your mind. Uh, Also, when we talk about keeping things straight in your mind, be neat, be organized, because oftentimes the largest culprit of mistakes was just terms getting dropped out and just general sloppiness. One thing I'd recommend is double checking again. If your probabilities end up being negative or greater than one, it likely means you have an issue. The third common mistake that we saw was students weren't reading the sentences that completely. So, example, 80% of delivery companies who use a consultant are profitable. Well, that's saying the probability of a profit given a consultant is going to be 80% or zero point 0.8. We're not saying the probability of using a consultant given a profit is 80%. That's not what we're saying. The probability of a profit given the use of a consultant is 80%. So when we start doing our analysis, we have to assign value scores for each of our alternatives. And this allows us to compare them and see which one has the greatest value to the stakeholder and which one has the worst value to the stakeholder. Oftentimes, we have to use a series of scales to convert the characteristics of those alternatives to a numeric score. So sometimes it's very natural, and you can use a natural scale. And that's, for an example, if you're looking at profits. So if you have dollars and profits, that kind of, you already have a numerical value right there. Now, however, more often than not, you have to use an artificial scale. And there's two types that we consider. The first is proxy. So a proxy scale is a reasonable, readily available substitute. For example, if we're looking at academic performance, we often use GPA as a proxy artificial scale for capturing your academic performance. However, sometimes things aren't that clean and you have to use what's called a constructed scale. A constructed scale is basically a user-defined scale where you set values in there, say 1 to 5, for how well each of your alternatives performs meeting a certain objective. Once we already know our values and objectives, as well as our alternatives, we can start actually modeling everything out. The two primary methods that we've discussed in class are influence diagrams and decision trees. So first, let's talk about influence diagrams. So influence diagrams are a series of nodes where we show the relevance that those nodes have towards each other. So there's 4 primary types of nodes. We have decision nodes, anytime we make a decision. We have uncertainty nodes, anytime that there's a uncertain event or unpredictability into it in the equation. We also have intermediate consequence nodes or calculation nodes, and we often use those when we have sub-objectives that we're trying to meet. And then we have our final value, our final consequence. Keep in mind that you can only have one value, one final consequence, one diamond in your influence diagram. If you have multiple objectives you're trying to meet, say you're looking at problem set 2, the final problem where you're looking at your deployment loadouts. In that case, you had 3 different sub-objectives to meet your one final objective of trying to maximize the effectiveness of the loadout process. You had 3 different intermediate ones. You would use the intermediate consequence nodes for each of those, and then they would feed into your final consequence. So y'all are generally good about identifying the different types of nodes and whatnot. However, what tends to get confusing are the arcs and how to draw them. So there's 2 primary types of arcs. The first is a sequence arcs. A sequence arc only points to a decision node. And what it implies is whatever the predecessor is has been resolved prior to that decision. So that means if it's a decision node pointing to another decision node, that first decision node has already been made and you know the outcome prior to having to make that second decision. If it's an uncertainty node pointing to a decision node, it means that that uncertainty has been resolved. You know the outcome of that uncertain event, and now you're using that to drive your decision. Now, a relevance arc is different. An irrelevance arc points to an uncertainty node a intermediate calculation node, or your final value node. And as the name implies, it just means relevance. So let's start with uncertainty nodes. So an uncertainty node has a probability tied to it. If the probability changes due to the predecessor, say another uncertainty node or a decision node, you would need a relevance arc. Um, for intermediate calculations or outcomes, if the outcome is based off of a decision or the uncertainty, it should point towards the to that node. And at the end, the value node, if your decision, if your uncertainty or your intermediate calculation impacts that final value, you should have an arrow pointing there. So here are some common mistakes. So with influence diagrams, make sure to remember they are not flow charts. They can easily be mistaken as flow charts because your decisions are typically sequential in there because you have your sequence arcs. However, the relevance arcs are not necessarily sequential. So right here you can see 3 different examples of influence diagrams, and this is based off of the quiz results. So you have a 20K investment, part owner decision, and they both impact your company's success, which then impacts your returns. They're not just a flow chart. You have to account for that uncertainty in there. There will almost always be some sort of uncertainty node. So make sure to think about that and include those in there. Decision trees are generally more straightforward than influence diagrams. And basically, you have a series of decision nodes and chance nodes. So a decision node implies that you have a series of different paths that you're trying to decide between. And you can pick any of those paths, and you're likely going to pick the path that gives you the best outcome. Now, your best outcome is going to be dependent on the chance nodes. So as you work through a decision tree, you should have some chance nodes. For each chance nodes, you have a series of paths that come out. Each path has a certain probability of occurring. So in this case, on the top example, you can see that there's 3 possible outcomes. Outcome 1 has a 50% chance, outcome 2 has a 30% chance, outcome 3 has a 20% chance. The probabilities have to sum to 1 for it to be collectively exhaustive and mutually exclusive. And at the very end, you have your payoffs or outcomes at the very end of your pathway. One thing to remember is that you have hash marks that are indicated in green on here. That indicates that once you finish your analysis, that there are decisions that there are certain paths you're not going to take because it gives you worse results than taking a different path. So make sure to include your hash marks. So what you typically use for determining how well the outcome is from a decision node is expected value for each of your paths. So the expected value is the weighted average of the possible outcomes, the weight being the chances with which the outcome occurs, and that's just straight out of the book. So in this decision tree you see here, you can see a chance node where you have a 10% chance of negative 100,000 and a 90% chance of 12,000. So if you take 0.9 times 12,000 plus 0.1 times negative 100,000, you end up with an expected value of 800. Now, if you take that path and go take that bottom path, you have an expected value of 800. If you take the top path, you have an expected value of 0. So you would take that bottom path, so you have your hash marks there to indicate that you are not taking that top path. So everything's pretty easy when you start looking at single objective decision analysis, but when you start looking at multi-objective, it gets a little dicier. So what you have to do if you're looking at multi-objectives is you have to look at what are your objectives. In this case example, you're looking at salary and fund level, and you have to convert your salary and you have to convert your fund level to scores between 0 and 100, and you simply just use value functions to do that. You assign your worst number a value of 0, your best one a value of 100, and you create a function between the two to allow you to calculate out scores between 0 and 100 for each of your outcomes. Once you build your value function, you can simply map out your raw score to the value. So in this case, you can see that 4580 maps to about a value score of 80. A fun level of 5 maps to a value score of 100. So we can do that for every one of our alternatives and get a value of 0 to 100 for each of our different objectives. However, you will notice that we have two objectives, so we have to now do a weighted average of the two to be able to get one overall value score for that alternative. So now you have to determine the weight for each of your value measures. So the weights for your different value measures have to sum to 1. And now what you can look at is just algebraically, you can say that, hey, one of the value measures is 1.5 times as important as the other one, and then you can solve it out algebraically to determine the two weights to use. And once you know the weights, you can simply multiply each of those individual value scores by that weight, sum them, and that gives you the overall value score for a given alternative. So we talked about single objective and multi-objective decision trees. We've talked about influence diagrams. It's useful to actually look at, hey, can we go between the two? And the answer is yes. So when we're looking at converting influence diagrams to trees, you have two typical cases to consider. The first is where you have the top one, where you have a decision and it impacts the probabilities on an uncertainty node, and both the decision and that uncertainty node impact your final value. So in that case, our tree looks like this, where the probabilities of the chance nodes change based off which decision we make. We also have the case of a basic risky decision, which you see in the second column here, where you make the decision, but independent of your decision is your uncertainty node. So this is like if you want to go hiking and the weather is pretty independent of whether or not you decide to go hiking. In that case, your decision node, up, down, has the same probabilities at the value node. So here you can see that top node has a probability of P, bottom node has a probability of 1 minus P, and same for if you make that second decision. So for example, if you look down here, you can see the classic example that we use, whether or not to get a shot, whether or not you acquire COVID this season. So the probability does change based off whether or not you get the shot. And so you can see that the probabilities in the decision tree change as well. We spent the last few classes talking about precision tree, which is a super useful tool. It allows you to build out decision trees, build out influence diagrams, convert between the two, but most importantly, it allows you to do sensitivity analyses. And what sensitivity analysis does is it allows you to look at the change in results that occur based off variations in your assumed values for variables. And so we have a number of different ways of doing that. First, we have a one-way sensitivity analysis. So one-way sensitivity analysis keeps all of your variables constant except for one variable and varies that variable across a range of values. And then it looks at how that impacts the overall expected value. In precision tree, we have a choice between a sensitivity graph or a strategy region graph. If we do a sensitivity graph, it just shows you the overall expected value of your problem, of your decision as you vary your variable. If we look at a strategy region graph, it looks at your decision node and it says, hey, if I make a decision, what's the outcome as I vary my parameters? So in this case, you can see that we're varying the bid to play from 5 to 12. And on our decision tree, we would have a fundamental decision with two alternatives. The first alternative is captured by the blue line and shows that as we vary the parameter from 5 to 12, the expected value decreases. Meanwhile, the second alternative for our decision has no impact. So as we increase the bid to play from B2 from 5 to 12, around a value of 11, we would change the decision that we're making. Originally, we'd go with the blue decision. As we pass 11, we would go with the red decision. The other one-way sensitivity analysis diagram that we looked at was a tornado diagram. And what a tornado diagram is it's effectively an executive summary of a bunch of different sensitivity graphs. And what it shows you is it stacks up a bunch of different variables. It takes each variable, does a one-way sensitivity analysis on it, and looks at what it does to your overall expected value for your entire decision tree. It then places the variable that has the highest amount of variation. It takes the variable that results in the highest amount of variation in expected value and places it at the top, and then it places the ones that have the least variation in expected value at the bottom. So it looks relatively like a tornado. However, keep in mind that if you turn it on its side, it looks like a bar chart and it just represents the overall impact that each of these variables has on your overall expected value. While one-way sensitivity analyses are great, it's often useful to do two-way sensitivity analyses where we vary two variables at the same time. And this allows us to look at some of the cross-correlation and effects that happen from two interlinked variables. So what you do with this is you can see that your x-axis is one variable, your y-axis is another variable. At a given point, you have a set decision that has the best outcome. Now, if it switches to a different icon, it means that you're making a different decision. So in this case, if my revenue, if successful, which is my x-axis, is 20, and my probability of success is 30, I'd be making the do not market decision. However, if my probability of success increases to 80%, I would be making the market decision. Hey, I hope you enjoyed watching this video, and best of luck on WPR1.